understand why in this morning we are talking about fluids which is at rest, why they are not moving. So why what we are going to do is look at the force weights of the fluids, right? And then develop a very important equation which if you are doing building surfaces and also pipe something related to fighting, that equation is really important. Why? It is called hydrostatic equation. I will give you some theory, and then after that some applications and some stories as well. Alright, so next, first we come here and then remind you something about pressure. Okay, so what is the fluid pressure? Now remember last time we looked at a plate, and we have many particles bombarding on the plate. Now each bombardment actually create a force on the plane because the velocity change. The velocity of the particle change, and that change is a change of momentum within a short time. So we have force acting on a plate. Wow. Now the force will be uneven, or maybe even, or the force may be uniform or not uniform. So the average pressure is calculated by dividing the total normal force acting on a plane area divided by acting on a plane divided by the area of the plane. Why? So F force y equal to it should be pressure equal to force divided by the area. Okay, so nothing that difficult, right? Now we are going to prove something. Now, if a physical phenomenon told us that if we look at a fluid, a part of the fluids or a point inside a fluid at rest, right, and that thing is not, that tiny volume is not moving, and therefore the pressure on the pressure is balanced, right? So the net force on that point is zero. So now we are going to prove something which is also really important, and it is the basis on which we build up our hydrostatic equation. Okay, now let's look at let's look at a tiny volume shown on the screen. I put to actually connect it to my plane. Now what you see on the screen is a tiny, very tiny piston or something like that. Now you see delta y, delta z, delta whatsoever, or delta x. This delta here is delta y means a very small length, right? Delta in the y direction, right? In the y direction. In the x direction, we have delta x very small, right? In the z direction, we have delta z, which I think very small. Okay, very small. This is a very small particle, but very small volume of water, liquid, or a fluid. Okay, and now we look at the pressure acting on this plane, A, B, C, on this plane, right? Now this is a vertical plane on the in the YZ plane, right? And this is the pressure, right? The pressure is acting at this point. Now, because this area is very small, so we can assume that Px is uniform over this tiny area, right? Now, this can only be true if we are dealing with a really tiny surface. Right? If we are dealing with a large surface, then this assumption is not going to work. But this is physically weighted because if you think, imagine that you are dealing with a very small area then the variation of pressure over this area can be ignored, basically, very small, right? So we can assume uniform pressure on this wall. Now the same principle apply. The same principle apply to this triangle ADE, and also the same principle apply to this inclined surface, right? ABCD. Now we arbitrarily set the inclination of the plane ABCD to be theta, right? So what we are going to show you, that's just in the last slide, right? But this last slide, we are going to show you that actually Px equal to Ps equal to Py, and also Pz, or if there is a Pz, right, on the vertical triangular area. Right. So now we just look at the vertical component, or we just look at the force balance on the XY plane. Okay. So force balance, and next we are doing force balance. Right. So in the x direction, right? In the x direction, this is in this direction. So what is the force? First of all, we have this Fx here, right? Acting on this plane. So the force is Px delta y delta z, right? Delta y here, delta z is the area of this vertical plane. So far, so good, right? And then we have second thing. Second thing is we look at the inclined plane. Why? So the inclined plane is in this direction. The force is acting on this direction. Now pressure has to be acting downward, or acting on the plane, right, holding the fluid. So the pressure is always pointing towards ABCD, right? If you look at the pressure on this plane, right? It's always pointing towards the plane. All right. So you well, right here. Okay. So we resolve the force into two components, right? Now this is the inclined force. So one is vertical, the other is in the x direction. This vertical one is in the y direction, right? Okay, so this is in the x direction, which is in the reverse direction of increasing x, right? So we have a negative side here. Why we assume this direction is positive. Okay, so for this force, right, we have a negative component, right, in the x direction. So it's P, this is theta. So this is theta. Right. So P sine theta is this force. And it is acting on surface ABCD, right? The area is delta z, and this inclined length, this length of the inclined surface is delta s, right? So this is the force, right? Due to the pressure acting on this ABCD, right? No more force, right? We have just two force in the x direction. So far, so good. And then, of course, we understand from Newton's law of motion. What law? Well, Newton's second law of motion. Net force equal to mass times acceleration. And now, if you look, now this ax is acceleration in the x direction. Now, this is the volume of the prism under consideration, and this is the density, which is assumed constant, because again, this is a very small component, right? Very small component. So yeah, this density can be assumed constant, right? Okay, the density within this thing is constant. and this is the mass. Oh, sorry, this is the volume. Delta x, delta y, delta z divided by 2 is the volume of this piston. The piston. Delta y, delta x divided by 2 is the area of this triangle multiplied to the height or something like this, right? The depth or whatsoever you will call, right? Delta x, delta y, delta z divided by 2 is the volume of the tiny region that is which is under our consideration. And of course, this thing is not moving, and therefore acceleration is 0, and therefore this force equal this force. Right? Now we finish the x direction. So how about y? Oh, y direction. Y direction now. Direction y. Y. In the y direction, we look at here we have a force, right? Acting in the y direction, but this force is acting on this C, D, E, F, which is acting on the bottom plane of this piston. So similarly, delta y, delta x, delta z represent the force acting upwards. Now against the pressure force is always acting acting normally to a plane. Right? Therefore, if you consider this C, D, whatsoever, C, D, E, F, then the force has to be upward, right? So this is this force. Right. Okay. Now, we have a component. When we consider the force on the inclined plane. Force on the inclined plane, yeah. The force on the inclined plane, no good. So it's really difficult to write using the pen sometimes, right? Okay. So here we have a vertical component and a horizontal component. Now we consider horizontal component already, and now in the y direction, this is in the y direction, right? This is the component that we are going to look at. So this is again in the downward direction. Therefore, you see the negative side coming out again. Why this time? Pressure on the inclined wall times delta z delta s is the force, right? And then the y component, you can obtain the y component of that force by multiplying cosine theta. Well, this is theta, so cosine theta represent the vertical component this time. Right. Now remember, in the vertical direction, we have to consider the weight of the fluids. Okay, weight is mg. So g, gravity, acceleration due to gravity, density, you know what it is, right? This is the volume. So this term is the where is it? My pen. Why my pen? Yeah. This point, and this point, yeah, this is the weight of the fluids. Right? So weight is acting downward. Right, always. Weight, right? mg, right? So it's always weight is acting downward, right? So weight W, weight W. Right? Weight W is also always working acting downwards. Okay, so we have three forces in the vertical direction. One is the force acting on the bottom plate. Second thing is the force acting downwards on the inclined plane ABCD, and then weight of the fluids. And of course, the fluid is at rest, and therefore, why the acceleration due to gravity, acceleration is 0, and therefore total force in the y direction is 0. Why? So far so good. Right, so we have x and y. Now z direction, you can work out later on, right? Okay, but z direction is easy because it's pretty simple, right? So Exact direction is uniform. So in our example, now we look at this relationship. Now you can find this relationship. Delta S, which is the length here, and then we have sine theta, which represent delta Z. Right? This is delta S. So delta Y is delta S sine theta. So, right? And then delta X is cosine theta. Sorry, delta S cosine theta. Right. So after putting this, then you found really simple equation or two equations. You found two equations. One is this. One is you get it directly from this one, right? And then for this one, you have these equations. So now you can see PS equal PX, right? From this equation here, PX equal PY. Sorry, PS equal PX. Okay, one thing. Now, second equation, why you have a little bit complication here. A little bit complication, but this term, now delta X is very small, right? Delta Y is very small. So delta X times delta Y, now you can actually cause out delta X here. So if delta Y is very, very, very small, the effects of the weight is basically not significant. Okay, so again, we have PX. So we have PX equal PS, right? So we prove why PX delta Y, PX equal PY equal delta PS. So no matter which angle here, no matter what is the inclination angle, PX equal PY equal PS. So now you will understand actually pressure inside a fluid does not carry a direction, right? So no matter which direction you consider, the pressure is the same. Therefore, unlike velocity, pressure is a scalar. So pressure have no directions. The force have, right? Because the area acted upon by the force has a normal, right? So force is a scalar. Pressure is not. Pressure is a force is a vector, right? Sorry, a force is a vector and pressure is a scalar. Okay, holding as a question, right? Delta X delta Y divided by 2 is the weight. I think this is the weight, right? And we cross out delta Z like that. Okay. Now we can do similar treatment to the Z direction, and you will find basically pressure is at a point is it doesn't depend on the direction. So when you sink into water, right? If you consider yourself a very small, tiny particle, then the force acting, I think the pressure acting on each part of your body should be the same. Now, very important. Now I repeat, my pressure is a scalar, right? Because it doesn't depend on directions. Now velocity is a vector and force is a vector. Force equal to pressure times area. Why? Now remember, area is a vector in mechanics, right? Because area has a surface normal, right? Okay, so remember, pressure is a scalar. It's an important concept. Later on, we will be using this to develop our hydrostatic equation. Okay, wow, it come very quickly, right? Hydrostatic equation. Last week I showed you equation of state and then viscous force, right? And this is the third very important equation that you have to remember. Oh, now we have a very tiny fluid strip. Okay, very tiny on the screen. on the screen. Why? This is a really tiny strip of force at rest. At rest means it doesn't move, right? It doesn't move. Okay. And now what happened to the force acting on this tiny strip? It's not moving. So no matter which direction you are going to look at, the total force will be 0, right? Okay, so we arbitrarily choose the PQ direction, which is supposed to be easy to understand. Huh? Why? We don't choose this direction. This is you actually after that you have to do quite a lot of things. So we just look at a particular direction, and this direction is PQ is a very easy methods to show you the principle, right? And force balance, right? Okay, along this stuff, along this PQ, what are the force, right? First, we have a pressure force acting at the bottom, and we have a downward force acting at Q, right? And then P and Q, now you can see, right? P, the height of P is Z, right? The height of Q is Z plus delta Z. Again, delta is a very small, delta Z represents a very small area in the vertical direction. The length is delta L. Right. So far, so good. Wow. So what are we going to do? Force balance, right? Okay, now we are looking at the force balance along the PQ direction. Okay, so this is the force acting downwards. So we consider this very downwards, right? A force at Q first. So the pressure, now we here assume the pressure actually vary with Z. Okay, this is allowance. We allow the pressure to vary in the Y, Z directions. Why? So at this point, we have P plus a delta P. A small change of pressure is allowed here. Why? The original pressure at point P is P, and the pressure now, when you move up distance of delta Z, we will have a change in the pressure, suppose. Right? P plus delta P, a very small change in pressure. Now, not delta times P, right? Now, in this, in our fluid mechanics study, delta P is a small change in P, right? Now, sometimes you will find a big delta P, right, which also represents a small change in P. Right. So next, the force acting at this point is P plus delta P times, of course, area, right? So this is the force acting here. Right, next, well, this is obvious, right? This is obvious, this is the force acting at point on P. Now, the direction is different, right? The force is in this direction, right? The force at P is in this direction, the force at Q is in this direction. Okay, next is the weight, right? Now, remember, always, weight is the body force, right? It's always there. We have to consider weight, right? So weight is against both mg, right? Mg, and the mass is the volume, right? Volume is delta Z, delta L. This is the volume, right? And this is the density. So this one multiplied to this thing is the volume, and then so density multiplied to volume is mass, right? And then mass times g is the weight. This weight is acting downward, but has a component in this direction, right? Which you can quickly estimate it to be what else, right? Is a component like this. Now we resolve things into two components. Huh? Okay, so this force is this component, right? So we multiply delta beta to resolve this weight, resolve the component of the weight acting in the direction PQ. And so the thing is not, the chip is not moving, and therefore again it is zero, right? Zero. The total force is zero. So now we are now taking out terms, right? How to do this? We are now delta A is the same, right? So we can take away delta A, and then now we have delta P delta A. So delta P, this P times delta A component can be removed. So and then now this delta L theta is delta Z, right? Is delta L is here, and delta L cosine theta is the length delta Z, right? This is delta Z. Okay, this is delta Z, and this beta, and means that this is beta, right? So this is beta. Delta L is here. Yeah, very ugly. Okay, delta L is let's write it again. Okay, that's we have what's that? Let's write it. Okay, now this is delta S. Delta is delta. Come on, this is delta Z, and this is delta L. Well, and this is beta. So delta Z equal to delta L times cosine beta. Right, so this is delta Z. Now we show that this term is not there, right? And then A is removed. And so what you have finally is this really simple equation, right? So you just have to rearrange some terms, and you got something like this. The gradient of pressure is equal to negative ρg. So it means that if you are inside a fluid and then moving upwards, then the pressure will be reducing. Interesting, right? So this negative side tell you the gradient of pressure is negative, means the pressure actually is decreasing with increasing Z. Right. So far so good, eh? No questions? Then let's finish the hydrostatic equation first. Right. Now we assume now in our study, right? Water is incompressible, air is incompressible. So to some extent, right, we assume in a normal situation, air is incompressible and water is incompressible. Right? For gas moving in the pipeline, right? They're all incompressible. Right, so density is constant. And gravity, right? Gravity, of course, gravity is not a constant, but if you are talking about buildings, right? Building or normal situation, the change in the height is so small to give you a change in the gravity due to acceleration. So, rho density is constant, G is constant. Very simple integration gives you P plus rho G Z equal to a constant. Right, so how to determine this constant? And of course, what is Z? Height is a really interesting variable. Wow. Now, if you are asked the questions, right, what is the height of a building? That is an easy question, right? You just count from the ground floor to the rooftop, right? So the height of building is just relative, right? Now the height of the building is what you tell people. The height of the building, actually, you are talking about the location, the height location of your rooftop relative to the ground floor, right? Relative to the ground. So height actually has you need a reference to describe height. So height is arbitrary. So you can set sea level as a reference. You can also set the local ground height as a reference. Now you know when we're talking about the height of a building on a hill, on a mountain, and the height of the same building when you build at sea level, the height is the same, but the actual height of the rooftop, you see, right? Above sea level is different. So when we're talking about height, we need to have Z. Well, okay. Let's me finish this one, and then I will pause a little bit. Okay, so Z here is height, right? Pressure plus rho G Z equal constant, and so what is this constant? So very arbitrary, right? Now usually we will say if you are considering a fluid which is in touch with an air on the top or gas on the top, usually we will set Z equal to 0 as the surface at the fluid surface. Now, for example, if you are talking about water, right? Water, we will set Z equal to 0 at the interface between the water and the air, right? So if Z equal to 0 is the air, right? Is air, then pressure, the constant will be atmospheric pressure. So in Z equal to 0 is our reference. Then the constant will equal to atmospheric pressure. So if we denote H at the depth means below Z equal to 0. So Z equal to negative H, right? And so this is the pressure of the fluids at a depth of H, right? And this is the reference. If you're talking about the reference, well, we make the reference at the liquid air interface. So if you are diving into water, right? And then if you dive to depth of H, right? Then the pressure acting on you will be P equal to the atmospheric pressure plus the extra pressure due to the water. Okay, and now P minus P atmospheric pressure is the gauge pressure. So this is the gauge pressure, and then we call this small h head, right? Usually we call it head. We give it a name of. Now, of course, this is the depth, right? In later calculation, this is the gravity head. Okay. So I can see there are so many questions. Therefore, let's finish your question before we go on. Right now, this is the hydrostatic equation. Wow, very important equation. A star here, and you have to practice doing this. And the tutorial and my revision MC will be dealing with these things. Okay, let's stop a little bit and answer to your questions. Now there are several questions which are very good, right? Very good question here. So the first question I have is from Gok Ho, right? Gok Ho, you are asking what is the meaning of Z, right? Z, I think you mean this Z, right? This is this is Z. Now this is Z in our discussion. We will go back to this. Go back to the last PowerPoint. What Z is height of P, right? Height. So Z is a height. Z depends on height. So Z represent height. But again, height is relative, right? So yeah, Well, Z is the direction, but in the vertical direction. Yeah, height. Z is height. Vertical direction in our case, right? Height. Vertical direction. Oh, I'm typing something. Z is height. Height, right? And then vertical direction in our discussion. Right. Next one. What is P mean in volt GH? No. What is that? I think I press a lot of buttons. What is P in PGH? No. Pressure here, right? Now because we have an equation, right? This is the equation that we developed. So let's write P. What's that? Well, P. Where's my pen? So we have P delta Z equal to negative volt G, right? So what you're going to do is to integrate this thing with respect to Z, right? So what you got is P equal to volt G Z plus a constant, right? Constant. So this is your equation. So P again, it's the equation. P plus volt. This is density. Volt G Z equal to constant. And so if you choose Z to be the pressure at the surface volt is density, right? This is density because this is density. We go back to previous slide right here. This is density. Density is density. It is the density of the fluids under consideration. How do you derive P plus volt GH equal constant? Right. So we based on our hydrostatic equation on the screen. P. This is what we have from the last slide, right? Okay. So this equation can be written as, if you integrate this P delta Z d Z, right? Out of dz. So you got your equations. But because this is an indefinite integral, so you have a constant here to be determined. And we usually set Z equal to H at the liquid and air interface. So at that location, the pressure is atmospheric pressure. So the constant is atmospheric pressure. If you put 0 here, the constant is atmospheric pressure. Okay, so far so good. Now, if Z equal to 0 is the liquid level, then we can denote. Yeah. Pressure at Z0 equal atmospheric pressure. Okay. Because Z equal to 0 is our air and liquid interface. Now we set it arbitrarily, right? Now because height is relative. Height is not our absolute variable. Height is relative. So just I give you an example, right? What is the height of this building? Then you tell people the height basically, it's 100 meters. Now actually you mean the distance between the ground level and the rooftop of that building is 100 millimeter. So 100 meters. So height is not absolute. If you just at the example I give you, you're talking about a height which is relative to the ground floor, right? So remember, a height is not absolute. This is relative. So usually in geography, right, we will use sea level as the reference. So the height of a mountain is that, and that means that the top of the mountain is XX meter above sea level. Okay, so remember when later on when you're talking about height, make sure that you have a clear reference data. Okay, now if we so we stick to our system, right? You said equal zero is the height of, so is the liquid level, liquid air level. So if you're talking about water, so you said equal zero is the level of the water and air interface. So if you are diving into water, for suppose this is water, why what air here, water, or this is water. And if you are, if you go down, the pressure here will be equal to this equation, right? And h is the height or the depth that you go to, right? So far so good, right? And this is the gauge. We call this gauge pressure. Now you will actually understand why this rho gh, if you look at the pressure here divided by some small area, right? You actually will realize that this term basically is the weight of the water above. If you are here, right? This represents actually the weight of the water column above your head divided by the area of your head, something like that, right? So we will show it later in the tutorial. So far, now before we go on, any more questions? Good. Yeah, let's move on. Now, sometimes we may be dealing with some compressible gas, right? So perfect gas. But it is not now for complete. I showed this to you for completeness, right? In building application, we don't have something like this. Or now, if you are talking about something, if your building actually start from the sea level to the top of the Himalayas, probably you have to consider something like this. Well, even gravity is changing. So in our building application, even you are talking about scraper or super scraper or super underground structure, right? We actually doesn't need to consider the compressibility of the gas, but for completeness, right, then we can have a discussion. Now, because for perfect gas, right, PV equal to mRT. Okay, so pressure equal to rho, this density time. Now this is gas constant, so it's constant. Temperature could vary, so we don't know. And P delta, the gradient of P equal to negative rho G, which is this is correct, right? We haven't assumed any compressibility or incompressibility of the fluid. So this equation work for all fluids, right? And because of this relationship, density is related to pressure. So you substitute P equal to rho m rho RT into our equation. You got a new equation, right? This gradient actually depends on pressure. The pressure depends on pressure. Wow. And then you integrate again. You do an integration, right? You integrate. Well, let's okay, right? So just integrate you integrate, right? You integrate delta Z here, so integrate delta Z. So you integrate, and then again, Z equal to 0 is the surface. Right? This is the solution that you will have, which is the assume temperature is constant, the pressure actually is exponentially decreasing with increasing height. Now what you have in the previous case is the pressure is decreasing like here. Oh, in the previous case, when we have a constant mole G, why the pressure actually is like that. Is that? Okay, this is in a way if mole G is a constant. Now for compressible gas, then you have these things. It's exponential decreasing. Why? This one is for compressible gas. Why, if we have a compressible situation, why the blue line represent the rate of the change of pressure with respect to change in the height. Why, assuming temperature is constant. Why, now if temperature is not a constant, well, and if the temperature vary with Z, then we can have this equation can still be integrated, right? No problem. Once you're given the how temperature vary with Z, and even how temperature vary with pressure, right? Now, that could be really difficult. But temperature vary with height, right? If we are giving a function of T variation with Z, then the equation can still be integrated, right? So, but this is out of our scope, right? In our building services or building application, right? Building application. We seldom deal with a fluid which is compressible when we are talking about fluid moving in pipelines, right? Or flow around buildings. We only deal with compressibility of fluids when it is in a compressor, right? Okay. So far, so good. This is for your completeness. Now, this P, now remember from now on, memorize this P equal to M out. So I would like you to memorize this. All right, memorize. P equal to rho G H, right? Now P represents the change in the pressure via, of course, plus a constant here, right? Constant, which is atmospheric pressure, usually. But in general, now just memorize this. P equal to rho GH, P equal to rho GH. P is the pressure relative to atmospheric pressure, or the change in pressure is a change in pressure anyway, right? Okay, the pressure change is when the P actually here is the pressure change due to a change in the height level of a fluid, right? So P equal to rho GH, P equal to rho GH. Now this is, yeah, memorize this, right? Now, in many textbooks, you will find a law called Pascal Law. Well, for completeness, I have to introduce you because you find this Pascal Law in many textbooks. Actually, it's P equal to rho GH. Okay, now what is Pascal Law tell us? The Pascal Law tell us the pressure in a fluid at rest is independent of the shape or cross section of the container. Now, for example, right, you have a container, wow, and you can see where this container has a very funny bottom profile, right? Very interesting, and it's water, and then you have this is the datum, right? This is the datum, height datum, this is reference, right? Delta like this is the reference, and P atmospheric pressure is here, and then you have water, and then here you have mercury. Right? Now mercury is heavier than water. I mean density of the of the mercury is higher than water, so mercury sink to the bottom of water. So what is Pascal law tell you? Now remember, right? Pressure is a scalar. So no matter you are talking about inclined plane like this, a curved surface, right? Inclined plane, curved surface, very irregular surface, the pressure is always normal to the local curvature. All right, always normal, like what you see here. Right? The arrow is always pointing normal to the bottom profile. So Pascal law tells us the pressure at A equal to the pressure at B equal to the pressure at C equal to the pressure at D equal to the pressure at E equal to the pressure at F equal to the pressure at G. Enough, right? This is basically what? This is basically a hydrostatic equation. Right? So they are saying the pressure along this line is the same. Pascal law. So it's our P equal to rho GH. Right? The pressure depends only on H. So if the depth is fixed, then the pressure has to be constant. So our hydrostatic equation actually is Pascal law. Huh? Next, you look at mercury. Right, so you have a little remark here. You see, right? So along this line, A, B, C, D, E, F, G, the pressure is the same. Atmospheric pressure plus rho GH. Now, the pressure at H, this point is different. Well, you have what else? You have mercury here. So pressure at H is higher because mercury has a higher density. So pressure at H is higher. Of course, the pressure, if this is this is still water, the pressure at H is also higher because of rho GH, right? Here the point H is at a depth where is further below the liquid level, right? So pressure at H is always higher than the point than those at A, B, C, D. Now you are reminded that although H and I are at the same level, while the pressure at H is higher because mercury has a higher density, right? So what actually is telling you is, why suppose this is A, this is A, and then this is B, I suppose, right? So if you're talking about the if you use the hydrostatic equations, right? So the pressure at A, the pressure at H, the pressure at H, the pressure at H, right, will be equal to the atmospheric pressure. Let's deal with the pressure at I first. Okay, pressure at I. Pressure is pressure at I equal to pressure, what? Rho G actually hydrostatic equation rho G B, right? We say this is B, right? Yeah. We say this is B, and then this is this is A. Okay. And then pressure at H. Pressure at H equal to atmospheric pressure, right? Plus rho GH, rho GA. Then also add into the mercury things. Mercury height is B minus A. Right? Yeah. Right. First we consider pressure here, and next we consider the rho GH, right? The additional pressure due to mercury. Now this is pressure due to this water column, and then this is the pressure due to this mercury column. So Pascal law is very straightforward. If you have hydrostatic equation, you explain Pascal law already. Could be really complicated at the moment, right? So we go to see some example. Let's some terminology first before we go to some example. Why? And here I give you, now you know density, right? You know mass, you know density, you know pressure. And in some textbook, in some textbook, you will find specific weight or specific gravity, something like that, right? Specific weight here. Specific weight is equal to the weight per unit volume, right? So it's density times G, specific weight, lambda. And you have specific gravity. Now, specific gravity is S, which is equal to the specific weight of a fluid divided by the specific weight of water at standard temperature. So if G is constant, then specific gravity actually equal to the relative density. All right? So no matter in the future, in this course, right, we take the acceleration due to gravity to be constant. So specific gravity actually is equal to relative density, right? So here you have some example, but this will be given in future calculation. So don't worry, right? Some of the students will ask last year, why this 9,816 Newton per cubic meter is the specific weight of water. Usually we take gravity due to acceleration equal to 9.81 meter per second square, and density is 1,000. So they do the multiplication, and they can't have this number. So it doesn't matter, right? This number will be given in the exercise or in the test. But usually, if this thing is not given, then just take water, have a density of 1,000 kilogram per cubic meter, and gravity due to acceleration is 9.81 meter per second square, right? So don't worry. Right? Now I emphasize again, we reiterate again, why specific gravity is equal to relative density if the G is constant. And in our program, in our course, G cannot vary. Sorry, right? Unless you go to Mars or unless you go to a very high such as you are on the top of Himalayas and the atmospheric pressure is so low and the gravity is a little bit smaller. Right? Okay, so I mean the acceleration due to gravity at high level is lower. So yeah, specific gravity equal to, you can just assume specific gravity equal to relative density. So if you are talking about a specific gravity of 10, it means that the fluid has a density 10 times that of water. Right, and then one of you asked what this is. This is SI unit, and this is, we are British unit, right? So doesn't matter. It's pound per cubic feet. So this is some old, British standard scale, which is not used in our course in principle, right? But it's good to have different units given. This Newton is SI, right? International, and this is old common scale. Yeah, that's a different in units. Okay. Now we talk about some simple application of hydrostatic equation. Now the first application of hydrostatic equation, of course, is to find out the pressure at a depth h under the water surface, right? This is interesting. And then the next thing is to find out the pressure of here is example. Now suppose I have a pipe, right? Inside the pipe we have fluids, and we would like to understand the pressure of the fluid inside the pipe. Right? This is our target here. A device called manometer is designed to do that. Okay, the design of a manometer is really straightforward. This is a YouTube. This is the manometer. Basically, it's a YouTube. Then YouTube here. I remember in my revision exercise, I have a little problem at the moment, so I haven't posted up the revision exercise. That will be next week, right? Early next week. Right. You will see quite some. I will give you some very simple estimation, right, to demonstrate the use of manometer. Really short questions, and of course you can go to the tutorial sheet as well, right? Tutorial sheet is more comprehensive. Right. Now the manometer basically is a inverted YouTube like this. Now in the YouTube you have a liquid. Now usually this liquid is liquid, right? And the liquid is heavier than the fluid inside the pipe, where the pressure has to be measured. Okay, so now this part is up to you, right? This part is sometimes this from the manometer, right? This part could be open to atmospheric pressure. So at point Q, the pressure could be atmospheric pressure, right? And then, so this pressure is known, but this is atmospheric pressure. Because this point is open to the atmosphere, so here is pressure equal to this, and this is air. Air is very light, and therefore the pressure at P, so the pressure at Q, what is atmospheric pressure? Okay. Now this column, this water, these fluids, all these fluids are at rest. Therefore, you can work our force balance. Okay. So we know the pressure at this point. Therefore, we will be doing a force balance, or now a force balance along PQ direction, right? Force balance. The area of the two rim are the same, so force balance means pressure balance, right? So pressure equality or pressure equilibrium, something like that. So force balance, well, in the future, I don't know whether some question will be very tricky. You may find in some case the rims of the two rims of a YouTube is have different diameter. Why? Now remember, if you are having that kind of exercise or questions, then remember we are talking about actually force balance, right? Only force balance, right, will help. Now in usually for YouTube, right, the rims are on the two. YouTube are symmetrical, right? So the rims or the two rims of a YouTube have the same diameter. So pressure balance become pressure equilibrium. This is well, just to remind you, if some case happen in the future, very funny case that you have two rims of different diameter. So we in that situation, remember, right, this is force balance, which is the key, right? The key thing to do. Right, so we're talking about force balance or pressure equilibrium for our case, right? So what are we going to do? Hydrostatic equation, right? Of course. Hydrostatic equation tell us the pressure at Q is this, right? No. So pressure at P, pressure at P equal to, now this time we have no what else? We have well, at this location we have a pressure. Suppose we have a pressure of the fluids inside, we call it pressure 1, right? Pressure 1 here. So at this point, we have pressure 1. And we have water column, mole GH. And then we have another column, mole GX, right? So pressure equal to pressure P at P equal to pressure at point 1 plus a column, mole, which is the density of the liquid inside of fluid A, okay? Fluid A is fluid A is in the pipe. Okay, density A, y, mole G, and G, Y, what? So mole GH. So which is the pressure at this point. And then we have an additional column of liquid B. So here you will have one more density of liquid B X. And we understand why here the pressure is balanced. Pressure is balanced when we have force balance, right? At along PQ. So P pressure at P equal to pressure at Q. So very quickly, we have P1 minus PQ plus this equal to 0, right? So if you are PQ equal to P equal to PQ, so this one here you put this thing to here, right? And then you have P equal to atmospheric pressure. So we could have atmospheric pressure to this, and this one PQ is atmospheric pressure. So P1 minus to PQ equal this, equal 0, right? So now in the handout you find I write just a small p here. This small p is the gauge pressure, right? Now remember small p from our previous working. This P small p actually equal to P1 minus atmospheric pressure. Right, again, this is our definition of gauge pressure. Right, remember our gauge pressure is the pressure relative to atmospheric pressure. Right, so we put gauge pressure equal to this. Right. So what you can, if you have Y, if you have X, if you have Y known to you, if you have X, they can be measured. Right. Then you can calculate the gauge pressure in the pipe, and you can. It doesn't matter, right? Like if you want to find the absolute pressure in the pipe, you just add the gauge pressure. You just add atmospheric pressure to the gauge pressure, and everything done. Interesting, right? Easy, easy. So easy, so far so good. Nice. Next, another example, more example. Now you have more. We will have more example later on. Right, and then another manometer. Manometer can help you to measure the gauge pressure of the fluid pressure in a pipe. Now, the manometer can also help you to work out the differential pressure along a pipeline. Like for example, here we have 0.1, right? 0.2, and the pressure here is 0.2. Sorry, P2. The pressure at 1 is P1. And now there are many situations that the fluid will lose its static pressure. Now in here you have kind of all of us here. So when the fluid come in, then they will suffer some loss. Later on we will talk about loss, right? When you go through some kind of structure like this, the energy of the fluid will be lost, right? So the static pressure will be lost. Okay. There are some other situations where we have very friction pipe or high friction here, which you will experience something like that in the experiment. Right, in that case, the pressure actually, the static pressure of a fluid is actually drop along the pipeline, right? And yeah, this is a very important kind of. I mean, the hydrostatic equation is very important in measurement. So later on, Professor Yang will tell you about this, and I will also tell you about this because it's so important, right? Now in this meeting, we look at how the kind of hydrostatic equation can help you to find out the measure the differential pressure along a pipe, no matter how that pressure, static pressure loss is generated. Right here is all of us, but there are so many different things that can result in a pressure drop along a fluid flow. Right? Okay, so a manometer you can connect the manometer to any 2 point in a pipeline, right? So here is pressure 1, and here is pressure 2. And you have a heavier liquid B, usually it's a liquid, right? Liquid B, and then you have a fluid A. Fluid A can be gas or can be liquid, but of course, this black liquid B is have a higher density. Otherwise, you create trouble. Right. So we apply our hydrostatic equation straight away. Easy. And we look at pressure balance along PQ. Pressure balance. Now I repeat. Right. If the beam here, the cross section of these two beams are not the same, then you have to look at force balance, right? But that is really funny structure, right? So it only appear in some it's not practical anyway, right? So usually in practice, the two beams are of same dimension. Okay, so on this side, the pressure at P equal to this, right? We have P1, and the hydrostatic equation x plus y is the height of the fluid A column above P. So rho GH, right? Again, P equal rho GH. So memorize rho GH, right? Okay, H is y plus x in this case. And if we consider the pressure at Q, well, the pressure at Q is like that, right? First, you have a pressure at pressure at P2. Then we have fluid A column, and you have a fluid B column. So this column gives you this rho GX, right? This time the H is y. Well, and then the fluid B column gives you this rho BGX, while X is the height of the fluid B column above Q. So they have to be equal because these two pressure has to be equal because the fluids B or the fluid in the U tube are at rest. So the pressure differential, the drop in pressure is P1 minus P2. Now usually pressure drop, right? So P1 is higher than P2, right? P1 minus P2 equal to density change multiplied to the G and multiplied to the height difference of the liquid inside the U tube, right? Inside the manometer. So far, so good, huh? Nice. I think you have no problem, right? Once you understand hydrostatic equation, these are basically a piece of cake. A piece of cake. This is interesting, right? Yes, a piece of cake means very easy. Right, so it's very easy. Next, isolate. Okay, so next we now we usually have, although this is a piece of cake, right? But you have to practice the calculation. Now remember, only practice make perfect. So practice more, and you will master the skills. And you need to practice, right? This is engineering, so you have to pay. You have to spend some time. Now, in-kind manometer is something that you will see in our laboratory, right? And the basic structure of in-kind manometer is like this. Now, this is what you see in the front, and you can also see, yeah, we have a vessel of liquid. Usually, we use alcohol here. Wet dye. This is alcohol with a wet dye here. So you see this liquid is usually wet liquid, probably alcohol. Now this in-kind manometer, you can see I have two rim. Now have two rim of different diameter. Now usually for manometer the two rim will be the same, but for manometer it is not. The manometer have basically a very big cross section here, vessel bar, right? The vessel bar, and then we have a small tube here for you to connect to some point in the pipeline. So you can, the in-kind manometer is to measure P1 minus P2, right? So the same as the manometer help you to measure pressure differential, and this thing also help you to measure pressure differential. But now manometer can be connected to a pipeline or can be connected to a device called pitot-static tubes. Yeah, Professor Yang will help you later on when introduce measurements. Right. So when now in this structure, remember, P1 here has to be larger than P2. Right? If P2 is larger than P1, then the fluid will move down and up into out of the vessel bar. But that is no good. So pressure here, boom, right? Add in, and then press the liquid into this in-kind rim where you see some readings. Now, based on this reading, we calculate P1 minus P2, and theta can be vary. In our laboratory, I think you have 3 levels. Theta has 3 levels, depends accuracy that you want, or the pressure, how small the pressure differential is. Right, so remember, right, you need to have some basic idea before you set your manometer. But don't worry, right, usually you start with the highest incarnation. Right? For the highest incarnation, the resolution is not so good, but at least you have some idea. You have some idea before you actually carry out your measurement. Then you can change the incarnation later on. Okay. Now the mathematics. The mathematics, I leave it to the tutorial. Wow. And we have to have a really in-depth discussion on this because hydrostatic equation is easy, but when it is when you go to applications, like for the previous 2 examples, hydrostatic equation can be easily applied. But for this in-kind manometer, when the rim, right, yeah, I can consider the reservoir as a one rim, right, and we have another rim here. The area is so different, and therefore we have to handle it with great care, and we are doing force balance here. Okay, I will leave it to the tutorial, and you can find more tutorial, more exercise about manometer YouTube in the tutorial, as well as the revision short question that I'm going to send you probably next week. Well. Okay, so far so good. Right? Now we finished hydrostatic equation. Not yet. Okay, hydrostatic equation actually so important. Now remember, P equal to px. Right, P is the pressure change due to height change. Okay, next, buoyancy. Right, when fluid, yes, when a fluid is now in. When an object falls onto a liquid air interface, Why? Some object will sink, right? Some object will flow. There's only two options. Okay, so now buoyancy is a phenomenon where or buoyancy is a situation where we deal with a force acting on a submerged body or partially submerged, partially immersed body. Okay. Now, when an object is now in touch with liquid, right, or fluids, usually it's liquid now. Air also, if this is a gas also, a force will be acting on this object because we go to we go to this, right? We go to this object. Our object is now floating on a liquid interface, two fluid interface. Now, when it is in this situation, right, actually its surface is receiving pressure from the fluids. Okay, so this is what happened when even imagine you are in the water. This is the situation. The pressure force is acting on you. So the resultant force is not zero. It depends. It depends. The resultant force is not zero usually. How can it be zero when you look at it? Especially if we do different fluids, right? We have no ways that the force resultant force can be zero. Of course, when it's apart from this, okay, let's put it this way. Now, this is the situation, right? And the buoyancy force equal to this. Now we have a formal proof of this, of course. Now, if you integrate pressure, something like that, right? Again, integrate pressure A, something like this. That is, you got the buoyancy force. Once you have the profile, right? If you have the profile, then one can. Now pressure is known, right? Pressure is something like about G H plus a constant. The constant doesn't matter this time, right? If you are talking about integrating on a cold surface like this, the pressure, the constant actually balance. If you integrate the constant or over all this surface, it keep you zero, right? So the constant doesn't matter. So this time is the rho g h which causes the effects. The h, at this point, h can be different, right? So on every point, actually, h is not the same. So after integration, you will have a force. Now, interesting, right? I can give you, if you are interested, then I can ask you to look at what happened when I is floating on water. And so you have the pressure, you forget the pressure of the air, and you do the integration, right? In that case, you found the buoyancy force actually is equal to this is the mass occupied by this fluid volume. Wow, this is volume of the object immersed in the upper liquid, and this is the volume of the object immersed in the lower fluids. Why? So density multiplied by this volume represent the mass of the lower fluid displaced by or displaced by this thing. Now remember, when you put an object in the water, that object displays water, right? Because it has to occupy some volume in the water. So when it is put in water, actually the water will be displaced. Now you can do a very simple things. If you have an object, like a marble, something like this. If you have water, you have a cup of water, you put the marble in the water, you find you have a glass of water, right? If you put marble or several marble into in the water in a glass, right? You will see the water level actually increase now because the marble occupy volume. So and right, so the buoyancy force is related to the mass displaced by the object, right? The mass of the fluid displaced by the liquid. So buoyancy force is this. Interesting, right? Let's go quickly. I have two interesting video for you. Well, this is just a remark, right? Sometimes the line of action or between the two forces may not be the same. That is, sometimes the force acting in this direction, sometimes the force will be acting in that direction. Now remember, you have a mass. You have your things, your object still have a mass, right? So if you take moment, then the moment above the center of gravity has to be zero. But it doesn't mean that the force of the upper part has to inline or collapse in the direction, right? The line of action of this upper buoyancy force need not to be the same, or need not to be the same, right, as that of the force acting on the lower part of the body, right, or lower part of the objects. But if you take moment above suppose it's stationary, then if you take moment at the center of gravity of the object, the moment has to be zero, otherwise this thing will take, right? So these are minor remarks. Right, next, this is the last topic, don't worry. Force on submerged objects. Right, oh, we have a little problem in the equation, but doesn't matter. Now in this sample slide, we will look at the force acting on a submerged object. Submerged object means it is inside a liquid, inside a liquid. Usually it's water for building surfaces and civil. Well, civil students usually look at dam, right? Dam, yes, dam, something like hydraulics, dam, coastal. Wow, okay. Now, in this discussion, we don't consider the atmospheric pressure, right? Submerged object. Usually, AI is here. We don't have to consider this atmospheric pressure because it acts on two sides. I suppose this is the submerged body, and this is just the cross section of that body, right? Okay. So actually, the atmospheric pressure is included on both sides. So even you include the atmospheric pressure in the calculation, it cancels out eventually. So we don't have to we don't have to include the atmospheric pressure. So we are going to deal with only the gauge pressure, right? Which is a pressure excluding the atmospheric pressure, which is a constant. Okay, the force acting on a small body here, the small force, right? Acting on a body at a depth h, right? H is rho gh, right? Rho gh the pressure, right? A is the delta A is the area. So the tiny force acting on this part of the object, right, is a plate. I suppose it's a surface, a plate. Okay. Rho g equal to rho g delta x force equal to rho gh, and quickly this is the y is this, right? Y is here. So y is sine theta, beta is here. So we could just convert h into y cosine beta. So we are going to find out the total force acting on the upper side of the fluid is this, right? The lower side, well, upper side first, right? We are looking at a force acting on the upper side, right? And so we integrate the whole surface, integrate the force over the whole surface, and this is what we have. Y dA dx. Now remember, we can also do it in the y direction, in the x direction. So, so this thing is we call it the first moment of area above the x-axis. Okay, so we can do this in the y direction, and so this is a we define. Let's put it this way. We define a centroid like x bar is the centroid. So the centroid of this object is multiplied. A is the definition of the things, right? So the centroid is area of the centroid, and this is the first moment of area above the x-axis. So we define a centroid like this, and the force is something like that. And the force, the total force acting on the plate will be F equal to rho g sine theta A times this one. Right, so depends on what area it is. Now don't worry, right? Why this centroid Y can be worked out once we have the area profile, right? You need to understand what is the surface look like, right, before you calculate the Y bar here. And now we also can take moment, right? If we take moment, then we take moment at point O, and the total moment M is something like this. And here we have a second moment of area here. And so one can define one more thing, is the center of pressure. The center of pressure is something like this, and we have this formula, and this is the second moment of area. You can see why. And the center of pressure, that is where the pressure is acting, right? The center of pressure, the center of mass is where the mg, right? But we are dealing with force, so we would like to look at actually where the force is acting, right? The force here, the overall force, right, which is defined using moment. Here, the location of force, which is defined by the center of pressure, actually is given in this expression, which is the second moment of area divided by the first moment of area. Now this is expected to be where the overall. Now if you the pressure, the plate is the pressure actually is acting on the whole plate. But for simplicity, if you want to just look at the overall effects of this pressure force, then you can first work out the total pressure force, and then find out where the center of pressure, and in the later calculation you just can assume that the total overall pressure force is acting at this center of pressure, and then you don't have to integrate over the whole surface again. Now this Y pi or Y bar, right, the centroid, the small centroid Y bar here. First put the centroid, the centroid of the surface, like these things, and also this center of force, which is the second moment of the area, actually can be found in tables. So don't worry, if you don't know how to do the integration, it doesn't matter. Well, you can find out it from table, because for any standard surface, like circle, triangular, rectangular surface, these are all known. So you can find it from tables. Now, of course, I would encourage you to find it using a fundamental methods, which is what I'm going to show you in the tutorial, right? The fundamental methods is to equate force and moment, right? Just as what we have done in the first place, right? We found force by doing integration, and then we found moment by doing integration. Now, this is universally, this approach is universal, right? No matter what surface you are having in the future, right? You can have you can work it out. Well, of course, you may ask, hey, Professor Deng, nowadays we have a computer. Yes, you are right, right? All these finite element computer can help you to find out all these kind of second moment and first moment, or centroid of surface, or center of pressure, just by finite element integration. Once you are given the profile, then everything done. You're right. But you have to know the principle, right? You are supposed to be our future and our future leaders, and so you have to know the principle, right? The principle is here. Apart from looking at tables, then you understand when we look at force on submerged object, we look at the force together with the moment, right? And we here, for simplicity, we define something called center of pressure and centroid of surface, so that we can have all these standardized and then look up from table. But in principle, right? But this is from the in principle, why it is all from a pressure, from the pressure, force, and the moment consideration, right? Okay, now we will have a tutorial example on these topics. Now the last thing, I think I'm not going to talk about this in detail, right? Because today we are talking about fluid not in motion. But for completeness, just look at what happens when the fluid is accelerating, right? So what we are going to do is to have a force equal to mass times acceleration, and this time acceleration is not stable. So what you are going to have is something like this. Now, when you look at this, compare this with hydrostatic equation, basically you found this expression is in line with our hydrostatic equation, because in our hydrostatic equation we look at y direction, and y direction have in the vertical direction we have acceleration due to gravity. So the pressure gradient in fluids moving with constant acceleration is shown in this equation. Basically, you will see actually the pressure is the acceleration is positive, then we are having a pressure gradient which is negative, right? This is the things that come out from this part of the discussion, right? So you can do the same in the y direction, and then things like, yes, in the z direction you have something like this, right? Now remember, z you have a body force, and then if you have extra acceleration, this is the new hydrostatic equation that you have to use, right? Provided that AZ is constant, then you can work out quite a lot of things. But this is outside our scope. Right here is just for completeness, and so I would like to end this part of the discussions. Now next, I'm sorry we are running out of time, but I'm going to show you another things, which is introduction on the application of hydrostatic equation in practice. Right, I give you I show you this I show you what? I show you the manometer, which we use to do pressure measurement. But there are some practical example which is really important, right? So I think you can see it, right? So this is like several slides, but I will do it very quickly. Now the first one is a video. Now in this video, there's no sound, right? There's no sound in the video, but there are some English subtitles. So let's look at this. Pay attention to what in the subtitle. Okay. This video has no sound, so don't worry if you cannot hear any sound. Right? Oh, see. What else? Yeah, no. Where am I? Oh. I hope that I won't accidentally go out of That is very bad, right? Okay, let's do that. Well, now that video is always on. It's always on YouTube, so let's do it quickly. Can you see it? Yes. Now this video doesn't have a soundtrack, but you should be English subtitle. Right. So you have a bottle here, and then you have a cap, and then you have a pin, which make a hole right, at the bottom. Now here you have some water jacking out. Right? If you cap, right, then no matter if you put the cap on, then no water come out. Right? If you release the pressure, water come out. So quickly, I think that's it. That's it. Yeah, that's it. And then if you put the cap on, the water stop going out of the. So the question is why the water stop going out of the hole when the bottle is capped. Okay, try at home. Why? So just stop. We stop. Nice. We go back to our PowerPoint. Okay, so the question is why we have no liquid flowing out of bottle if the cap is on. Now you may ask why hydrostatic equation. Now first of all, why the liquid come out if we doesn't have the cap. Now why if we don't have the tap on, then the pressure at this point, right? The pressure at this point, okay, no, why? The pressure at this point, pressure equal to OGH, right? OGH, exclude atmospheric pressure. Now, because atmospheric pressure is here and atmospheric pressure is there, right? So the two pressure balance. So when we open the cap, then the pressure here is pressure equal to OGH, right? So no water will come out because the pressure here is higher than atmospheric pressure by this amount. So water is forced out of the hole, right? So no problem. But with the cap on, why the foot is not moving? You will say, here you still have OGH. OGH. So what is the problem? What is the problem? Now remember, right? When here we have a cap, the pressure at this point is not only OGH, right? For example, we have a pressure A here. So pressure A plus OGH is the pressure at this point, right? Now when you first cap, when you still have water coming out, I think you cannot realize. So you look at the video carefully. Why before it stopped, before we actually close this cap, you still find some liquid coming out. So actually, the pressure here is very small. Sorry, the pressure here is more than atmospheric pressure. So eventually, the fluid will stop moving once we have something like this, right? So this pressure plus this column OGH equal to atmospheric pressure. In that case, no water coming out. So once you cap it, if the pressure is still atmospheric pressure, you still have water coming out. But because when water coming out, you have larger and larger volume of gas air above the liquid. Eventually, the pressure is fall below atmospheric pressure. So eventually, this will happen. Now remember, right, density of liquid is so high when compared to air. So a very small reduction in the area will give you a very large change in the air pressure. So the pressure stop going out when we have a cap is all because we have a kind of lower pressure, air pressure here lower than atmospheric pressure. Okay, so when we open, then no choice. Open here, the pressure here must be equal to atmospheric pressure, and the net pressure, right? The net pressure is rho gh, period, right? This time, force come. This liquid is being forced out. Interesting, right? Next, now this is building. Oh, this is a building. Now on the top, I don't know whether you know, right? On the top, you have a water tank usually. I mean, in most of the case, you have a water tank. So actually, the water is pumped up to the tank, right? Why? Now this water stored in the tank in order to give you constant supply of water. Now you can imagine if, or even the tank here is not only for domestic water, it's also for sprinkler water actually. Right, so there are water tank here, some for sprinkler, some for domestic water supply, right? Tap water, something like that, right? So fresh water, all this, right, all here. We have pumps. Now we need water storage on the top of the building because we cannot actually every time switch on the pump when you switch on your tap, right? When you open your tap, then we switch on the pump. Then the pump has to be right? So many people actually open their tap at different times. So if you do that, if you have a pump, right? If you don't have a reservoir on the top of the building, then your pump will be by putting on and off many times and it break down within 1 hour, right? In that case, the water is something here. We have water. So when you open your tap, this water is which is at the rooftop, right? High position. And then if you are here, right? If you open the tap, then the water. Now sometimes for lower floor there will be pump coming up, right? But for the higher level floor, like here, if you are staying here, then the water comes down because of rho gh. Again, rho gh. You don't have to turn on anything. You just have a pump. So you just have water here, and the water, if you open your tap, right, the water just comes down like this because of gravity, rho gh. Okay, so it is kind of energy saving, and it also protects pumps, and it also can maintain a quite good quite good and steady supply of tap water. Sprinkler water. Sprinkler is smaller, fresh water. So it's when you now you are not go to the rooftop, of course, right? But on every building, so there should be a water reservoir on the top of building, and to serve or to maintain the water supply, steady water supply at basically at the upper part of the building. Right? For lower part, maybe pump. Right? On the upper part, you have big reservoir, and remember, rho gh help you to hydrostatic phenomenon help you to get water supply from the reservoir. Right, interesting, right? Next, we have another video called buoyancy. You have a question. Later on, we will deal with this. Okay, next, then we look at another video, right? Called buoyancy. I don't know how long it is. Should be very quick. It's very interesting. But the gentleman, now no matter you like him or not, the gentleman is quite I don't know how to say it, ugly, something like that. But what he say is really true. So I would like to share this PowerPoint as well. You may not like that gentleman, but just listen to what he said. Right here, yeah, you have a soundtrack this time. So the video is the title of the video is Why Do Things Float?
Welcome to the Science Asylum. I am Nick Lucid. The question we're answering today, why do things float? It has to do with densities, right? OMG, our chemistry class is still pushing that nonsense? There are only 3 possible reasons this misconception continues to be spread by science teachers. 1, they don't understand it. I'd like to think they do as scientists, but who knows? 2, they don't think you can understand it. Let's face it, quite a few teachers and textbooks feel this way. Luckily, I do not. And 3, they're traditionalists. This is how it was taught to them, so that's how they're going to teach it to you. This act of stubbornness is a gross violation of what science education is supposed to be. I think it's time we put it to rest. But first, we need to know why density isn't enough to explain floating. Density is always given as a mass per volume, where mass measures how much stuff is there, and volume is how much space that stuff takes up. So it sort of measures how well a substance takes up as little space as possible. Now, density can vary a little bit with temperature, so the examples I'm about to give you are at room temperature. Copper is 8,960 kilograms per cubic meter. Aluminum is 2,740 kilograms per cubic meter. Glass is just under that at about 2,500 kilograms per cubic meter. Water is 998 kilograms per cubic meter, which we usually round to 1,000 to keep it a nice round number. Gasoline, 730 kilograms per cubic meter. And last but certainly not least, mercury sits at about 13,600 kilograms per cubic meter. Holy mercury, Batman! I know, right? That's just crazy! Larger numbers for density means the substance is better at fitting into a small space. Experiment time! I'm going to place this piece of ice, skull, into this glass of cold water. Bam! It floats. I can even push it into the water, and when I release, it floats back up to the top. Yeah, 917 is less than 1,000, so it floats. Gah! That's a nice trick, but what happens if you replace the ice with Ninja Ducky? Oh, here's the problem. Ninja Ducky is made of soft rubber, which has a density of about 1,100 kilograms per cubic meter. That's 100 bigger than the value for water, so the density rule says Ninja Ducky should sink. Debunked. Also, if you did this experiment in space, you could put Ninja Ducky anywhere in the water and he wouldn't move. Yet he still has the same density up there. Floating isn't actually about density at all. It's about weight and pressure. Weight is how much Earth pulls down on things with gravity, which is a very familiar concept to most of us. Now let's see. Ninja Ducky is about 13 grams or so. That comes to a weight of about 0.03 pounds, or 1/8 of a Newton. When you place him in the water, his weight pushes some of that water out of the way. See? He's submerged a little. However, the water has weight too, so now Ninja Ducky and the water are in a battle for supremacy to occupy that space. The heavier one will win. In this case, that's the water, and Ninja Ducky floats. Pressure comes in when you want to be a little more mathematical. That's usually stated as a force distributed over an area. We can represent that with a bunch of little forces, like the ones around this ball. Notice the forces are bigger on the bottom than they are on the top. This is because pressure increases with depth. Skeptical? Consider the scuba diver. The pressure on the diver is due to the weight of the water above. As the diver goes further down, there is more water above them, and therefore more pressure. Okay, back to the ball. We can add all these little forces together, but we have to be careful about direction. So we'll split them all into 2 pieces. A quick look at the horizontal pieces and you can see they all cancel each other. The vertical ones don't cancel because they're bigger on the bottom. They push more up than they do down. So adding them together results in this, which is called a buoyant force. According to Archimedes' principle, the buoyant force on an object is always equal in strength to the weight of the fluid being displaced by that object. In this case, the fluid is the water and the object is Ninja Ducky. Remember, we said they were in a battle for supremacy. However, in Archimedes' principle, the fluid and object could really be anything. It doesn't even have to be an object that floats. This bowling ball has a buoyant force on it too. The ball just happens to be heavier than the water, so it sinks. So the next time someone tells you floating is because of density, make sure to correct them. Things float because of weight. We don't want to keep perpetuating that horrible myth. So what's the coolest floating experience you've ever had or seen? Please share in the comments section. And until
okay, fine. That's very interesting, and that's enough. So you want the whole story how and why object flow on a liquid. So let's get a little bit summary, right? So I repeat the question here. So why B duct flow on water? Right? B duct. B duct. What is B duct flow on water? Okay. So the first question is it density? Is it because of density? Now I'm going to do some polling, and so let's test some of your concept here. So just choose or false, right? Choose or false. So first of all, now is density. Why B duct flow on water? I'll start doing why B duct flow on water. Its density is less than water. Yes or no, yes or no, yes or no, yes or no. Its density is why an object flows on water. Its density less than that of water. Yeah, this is a very tricky question. Okay, so you have a comment here. I have another section, so I leave early. Okay, sorry. Okay, so if you have some, this PowerPoint will be actually we are close to the end. So if you have and some lecture to attend, please yeah, I will see you during tutorial. Okay, so this is a tricky question. Why an object flows on water? Okay, any more response? Now let's solve the response. So I solve the response. Now here, interesting. Now if the object have the density lower than water, it sinks. Oh, sorry, it flows all the time. So I'm not asking. The question is why an object flows on water. I'm not. This question is not on B duct. B duct density of course the density of B duct rubber is higher than water, but the density. The question is yes. The answer is yes. If the object have a density less than that of water, it flow all the time. Right? Okay. So remember, right? The question is yes. The answer is yes here. Next. Okay, and this one is it N? And this one. Okay, next when we look at another. Yeah, next. The next question you actually see on the screen. So what is if object its weight is less than the water display? Oh, where is it? So this one. So an object flow when its weight is less than that of the water displaced. Quickly response, please. Another difficult questions, right? So an object flows on water because its weight is less than that of the water displaced. Any more? Okay, let's stop the polling now, and you see why is it? Now, if the object flow on water, right, the weight, why it flows, if the weight is less than water displaced, then it will fly off. Right? So when an object fall in the water, yeah, I will pass this PowerPoint because there are some question answering during the teaching and learning process. So I will upload this video after we do the discussion, right? So no, don't worry. The answer is no. Why? The weight of the object is equal to the water displaced. We cannot be less than. Otherwise, it doesn't make sense. Right? If you put if the object like B duck here, right? Like B duck, like the B duck, right? Like the B duck, right? Actually, it's when it is on water, it displays the water. So if it flows, the weight of this B duck will be equal to the weight of the liquid water displaced, not less than. So here is the answer. Okay, so next one is when an object sinks. Wow, same thing. Right? An object sinks. The first question is its density larger than water is sink? Sorry, Bo, one a little bit. We have only one more slide. Well, two more slides. Yeah, let's show the result. Here, let's show the result, right? We are running out of time. So show the result. Now here, well, I hope you can listen to the video again, right? If it's when object sink into water, its density is larger than the water. Well, it depends. So A is not always true. So I will say no. It's not always true, right? Just like B duck with rubber. The density of rubber is higher, but it falls on water, so it doesn't sink. Just like Ninja Ducky, right? in the video. Okay, next one. Just next polling is this last polling. Yes. So an object sinks when its weight is larger than that of the water displaced. It sinks.